All right. Hello, everyone. I hope you guys are doing good. So the topic of today's discussion is going to be around this technique, which is called as the sweep line technique. So this is a kind of well-known technique, and it can be used to solve a variety of very cool problems involving intervals and stuff like that. So yeah, today we'll be solving 3 problems based on this technique. And yeah, before that, I'll start with the brief introduction of what exactly this technique is and in which situations can we apply this technique. Okay, so let's start. So let's start by defining what exactly is this sweep line technique. Okay, so it is a technique which can basically be applied in problems in which you have some intervals and you have some starting points and some ending points for each interval, and then you have to figure out the value of an expression. Okay, so this technique is useful when you have some intervals and you have to figure out the value of some expression. Okay, so by intervals, what I mean is a set of values which comprise of a starting point and an ending point. So we have n points of this. We have n points of this type. So every point is basically a combination of a starting point and an ending point. And it means that an interval starts at the point x equals to li, for example, and it ends at the point x equals to ri. And we'll be given with n intervals of this type. And somehow we have to figure out the value of some expression which varies from problem to problem. Okay, so that's our goal. Now, what exactly is sweep line technique? So in sweep line technique, what we do is we basically iterate on some x coordinates and try to maintain some data structure and try to maintain some information. Okay, so what we'll do is we will iterate on the x coordinates and try to maintain the relevant information in some data structure. Sorry. Yeah, so we'll basically iterate on the x coordinates and try to maintain some important information in a data structure. Okay, so that is the main goal here. Now the question arises here, which are the x coordinates on which we are going to iterate? Because in most of the problems, these li ri values are huge and they can be as large as 10 raised to the power 9 or even larger. So the natural question to ask here is, will we iterate on all these values starting from 1 to 10 raised to the power 9? The answer is no. So what we'll do is we'll basically only iterate on the relevant values of x coordinates. Now, what are these relevant values? So let's say we have n intervals and each interval starts at the point li and ends at the point ri. So if we put all these 2n points that we have, li and ri values of all the intervals, and we put it in a vector and then we sort these two vectors, then what we notice is that between any two consecutive points in our vector, nothing changes. There is no interval which is starting and there is no interval which is ending, right? So if we put these 2n values in a vector and sort it, we notice that nothing changes between x equals to, let's say this vector is a. So we notice that nothing changes between x equals to ai and x equals to ai plus 1. Why? Because no interval is either starting and no interval is ending between these 2 points, right? So the situation at x equals to ai, so let's say that ai is equals to 0 and ai plus 1 is equals to 5. So here what we notice is that the situation between x equals to 0 and x equals to 4 is exactly the same. So if we are considering x equals to 0, we don't need to consider any value from 1 to 4. So what I'm trying to say is only these 2n values are important to us. So we will forget about all the other x coordinates in between them. And the value of n is typically around 10 raised to the power 5. So this is advantageous for us because now we only have to look at these 2n values. So we only look at these 2n values. Obviously, 2n, this expression 2n is in the worst case. These li and ri values might have some duplicates as well. So at max, we will have to look at these 2n values only, and we will maintain some kind of data structure to store some information. Okay, so this might sound a bit vague right now, but now we'll start solving some problems and things will start making much more sense. Okay, so if someone has any doubt in this definition, you guys are free to ask. Otherwise, I'll just start with the discussion of the first problem that we'll be doing today. So yeah. Yeah. So does anybody have any doubts here?
Could you give an example with small values?
Okay. I think if you're looking for an example, the first problem that we'll be doing today, it is a very light problem and it will serve as a very good example for this technique. Okay. So it would be better to just wait for the first problem and then surely things will be much clearer.
Okay, sure.
Okay. Any other doubts here? So if not, I think it's a good time to start looking at the first problem. We'll be dealing with 3 problems today. And I have already shared the link to each problem in the Discord server, and I'll also be putting the links in the chat as I go through the problems. So Ansh is asking, sweep line is a data structure. So sweep line is a technique in which we use various data structures. Sweep line in itself is not a data structure. Okay. So let's start with the first problem. It's called Rescue Nibel. It's problem D from Code Forces round 672. I will just share the link in the chat box. Okay. All right. So the link is shared. Let's now read the problem. So we'll just ignore the first 2 paragraphs. So the problem basically says that there are n lamps with something, and this guy knows that the time of turning on and off of the ith lamp is Li and Ri respectively. So basically we have these n intervals and their starting points are Li and their ending points are Ri. And to open the door, we have to choose k lamps in such a way that there will be a moment of time when they all will be turned on. Okay. So our goal is to choose a set of k lamps such that there will be a moment of time where all these lamps will be turned on. So what that means is that we will choose k of these segments, and our goal is to take the intersection of these segments and make sure that that intersection is non-empty. Okay. Because if the intersection is non-empty, then there will be a point of time which will be there in all of these intervals, which means all of these lamps will be turned on. So our job is to decide in how many ways can we achieve this. Okay. So while Cyan decides which of these K lamps to pick, Ori is interested in how many ways are there to pick such K lamps. So we have to decide how many ways are there to pick K lamps out of these N lamps such that their intersection is non-empty. Okay. So this is the problem. We have to find this value modulo this prime number. Now let's focus on these constraints. These constraints say that the value of n is up to O of 10 to the 5. And these values of starting points and ending points are huge. They can be up to 10 to the 9. So this is a perfect example of a situation which I was discussing before. We have n intervals, and the expression that we have to find here is the number of ways in which we can pick k lamps such that their intersection is non-empty. Okay. And yeah, that's the problem. So now I'll give 4 to 5 minutes to you guys to think about the problem. And as in when you guys think of something, you guys are free to share. You can unmute yourself or you can write it in the chat box. Or else within 5 minutes, I'm going to discuss with the solution. Also, if the problem is not clear, you can ask any doubts that you have. Yeah, so the 2n values that I was talking about were these values. So we have an Li value and an Ri value for each interval, right? So in total, we have 2n values. So these are the 2n values which are important to us because anything which is not in these 2n values is just repetitive. So as you can see in this example, if we put all of these 2n values in a vector and sort it, and we realize that at one position there is 0 and in the next position there is 5 in that vector, then that means between 0 and 4, no interval started and no interval ended. So the situation at x equals to 0 and x equals to 4 were exactly the same. In this problem, instead of x, there is time. So the situation at t is equals to 0 and t is equals to 4. So the number of lamps which were on at t is equals to 0 and the number of lamps which were on at t is equals to 4 are exactly the same. So we don't need to look separately at t equals to 1, 2, 3, and 4. We just have to look at t is equals to 0 and then we can straight away jump to t is equals to 5. That's what I meant by only looking at the 2n values. So Sumit says we can try fixing the lamp and find the number of corresponding k minus 1 lamps. Okay. But how will you then find the k minus 1 lamps? Obviously, there is a very trivial way to do this. We can just look at all the expressions in which there are k lamps on, but the number of ways to choose k lamps from n lamps is nck. And in every way, we can just try to find out their intersection and check whether it is non-empty or not, and then increment our answer. But obviously, that is going to TLE. So we have to do better than that. Try to think about what I have just explained here. So JM says, yeah, so JM says we can sort the pair of Li and Ri values and use 2 pointers. If Ri of the first pointer is greater than or equal to Li of the second pointer, then if we have L length, we can add corresponding sections. So yeah, this is very close to what we are actually going to do. So yeah, great work here.
We could also use a map for this, right? While we insert the start and end points.
Yeah. We can also use a map.
At the start point, we could increase the count of the map. At the end point, we could decrease the count. And then while we iterate through the map, at the points where that count is greater than k, we could consider that as one valid.
Sure. Yeah, so this is another way of implementing the same solution. So I will show you the way of implementing using maps in the second question. So that way we will look at all the ways in which we can implement this. So in this problem, let's keep it easy. I'll only use vectors. And in the next problem, I'll use maps and implement it. Okay. So we can check for every time 1 to 10 raised power 9, how many are in this interval, our answer will increase. Yeah, so that's the problem. 10 raised power 9 is a big number, right? So Satyam, you are very close to the answer. Just instead of looking at all values from 1 to 10 raised power 9, we can look at these 2n values of that we have. Okay. Instead of looking at all of these time periods from 1 to 10 raised power 9. Okay, Gaurav says we can sort the LR when a lamp turns on and +1 if it is turning off moment. Yeah. And we can do it. We can do a prefix and find its k. Yeah, that's good. So this is something that we are going to do. So you guys are very close to what the actual approach is going to be. Yeah, so enough discussion. I think we can start with the solution now. Okay. So this problem is basically a straight application of what I have written above. So if a lamp is turned on, so if a lamp is turned on or off at t is equals to something, at t is equals to t naught, and the next relevant value is t is equals to t naught plus 5, let's say. So this is the same thing that I have written above. So out of these 2n values, the smallest is t is equals to t naught, and the second smallest, let's say, is t equals to t naught plus 5. Then we don't really have to look at t from t naught plus 1 to t naught plus 4. And the simple reason being that the situation at t equals to t naught and the situation at t equals to t naught plus 4 is going to be exactly the same. So we only have to look at these 2n values which are relevant to us. I hope this is making sense to everyone. So yeah, this is what we are going to do. So what we'll do is we will sort all these L values separately and we will sort all these R values separately. So we sort all L values in a vector R and all R values in a vector R. Okay. So this is what we are going to do. Now we are going to apply 2-pointer technique here. Why are the values same at L and R? I don't really understand your question. Yeah. So some intervals can end and some intervals can start. That is not a problem. We'll see how we can handle that. Yeah. So the values at t equals to t0 and t0 plus 4 are same because between t equals to t0 and t0 plus 4, no interval is either starting and no interval is ending. That means if an interval was going on at t equals to t0, it will go on at t equals to t0 plus 4. And if an interval had already ended at t0, it would have ended at t0 plus 4 as well. So the situation at t0 and t0 plus 4 is just the same. So we only have to look at t0 and not anything in between t0 and t0 plus 5. Okay. So now what we'll do is we'll apply 2 pointers. So Ayush says just a corner case at time t, suppose a lamp is turned on and another lamp is turned off. So at that moment were 2 lamp. Yeah. So according to the problem, they are saying that these Li and Ri values are inclusive. Or let's see. Okay, so these values are not inclusive, I think. So the lamp turns on at t equals to Li and it turns off at t is equals to Ri. So basically, we first have to give priority to turning on and then we have to give priority to turning off. So the answer to your question is that only one lamp was turned on because at t equals to these Ri values are not inclusive. If these values were inclusive, then we would have said that 2 lamps were turned on. But since these values are not inclusive, we will say that only one lamp is turned on. Okay. Okay. So now what we'll do is we'll apply 2 pointers. Okay. Yeah. So let's say one pointer I is for L and so I is for L and this J is for R. So we are at some value of I and some value of J. So there are just a few cases. So what we'll do is we'll maintain the number of lamps which are turned on. So let's say this is a variable lamps and we initialize it with 0. And at each moment, so initially I is also 0 and J is also 0. Now we apply this while loop, which says while I is less than size of L and R is less than size of R. Sorry, J. So now we have this while loop. Okay. Now what we'll notice is we'll compare these two values of Li and Ri. So if the value of Li is smaller than the value of Ri, Rj, so if Li is smaller than or equals to Rj, that means we have encountered a starting point of some interval, right? So then we'll do something. So if we have the starting point of some interval, that means a lamp is turning on at this point. So we can simply increase our lamps variable. So we'll just do lamps plus plus. Okay. Now we have a particular value of lamps. Now what to do here? Basically, we have to check whether K lamps have been turned on or not. Okay. So let's say that some value of lamps is there and we'll check whether this value exceeds K or not. And okay, so what we'll do is, so we'll check if these lamps are greater than or equal to K minus 1 or not. Because if previously the lamps were greater than or equals to K minus 1, we have another addition. So now they were greater than or equal to K. Okay. So now can anyone tell me to how many, by what value should I increment my answer? So I have this answer variable, which is initialized to 0. So can anyone tell me by what value should I increment my answer?
Lamps CK.
Lamps CK.
Combinations, right?
Yeah. So do you think lamps CK is the correct value? We have to find out the contribution of this particular lamp, the lamp which just turned on. So basically, we are making sure that
lamps minus 1, K minus 1.
Just a minute. Okay, so I haven't noticed that I haven't incremented the lamps variable right now. So it would be nothing but lamps CK minus 1. Okay. So answer plus equals to C of lamps and k minus 1. And then I will increment my lamps, of course. And then I will also increment I. Now, otherwise, what happens is that we have encountered the endpoint of some interval. So we will just do lamps minus minus and j plus plus. And then we will return the final answer. Okay, so I think this is the best explanation for this. The code itself is pretty self-explanatory. So this is the entire solution to the problem. Yeah. So we can
in the combination.
Yeah.
Go ahead.
So
in
we
the
can
combination. Okay. Sorry.
So we can increase the lamps first, and then we can also do lamps CK. That is the same thing. Lamps minus 1. Then we have to do lamps minus 1 CK. CK minus, yeah, CK. Sure. Okay. Just a minute. I think, no. So we can't just increment lamps first and then do lamps CK, because we have to fix that we are considering this ith lamp. Okay. We are considering the lamp which has just started at the point x equals to Li. So we have to make sure that we are considering it.
But then we can do lamps minus 1, k minus 1.
Yeah. That we can do, sure.
But do we need to specifically consider the ith lamp? Because as long as k are on, any k could be chosen, right?
Yeah, but we need to look at the contribution of the ith lamp, of this lamp which just turned on. Yeah.
I didn't get, why is the contribution of the current lamp important?
Because if you don't look at this contribution, then how will you justify this expression of choosing something? You are basically calculating the contribution of each lamp and then you are adding this value. But if you simply ignore the contribution thing, then how will you justify taking an expression? Because an expression is basically the contribution of something, right?
Okay. I was considering that at that point, if k are on, you can choose any k, but okay, you have to consider this one. And
that will result in overcounting.
Yeah. True. But let me think about it for a minute. I think we can do that. It won't change anything.
Because you should be able to choose any k if multiple are on.
No, but I get it now. So it will result in overcounting, and the reason being that between two particular values, we will sometimes count the same k set of lamps twice, and that can happen if we do that. Okay, so we have to fix a particular lamp.
Yeah, clear.
Right. So are there any other doubts, or can I go to the coding part now? I have the same doubt as Sumit. Why can't we? Yeah. So the reason being, if we just do lamps CK, sometimes what can happen is that between two values of between two relevant values out of these 2n values, we can sometimes choose this exact same subset of k lamps. Let's say at a particular value, there were k plus 10 lamps which were on, and then there were k plus 9 lamps which were on at the next particular value. So in these two values, I can, if I just do k plus 10 CK and then I do k plus 9 CK, it is possible that I will choose the same subset of k intervals twice, and I can't do that. Okay. All right. Okay. So are there any other doubts? If there are no doubts, I can just quickly code up the solution.
But that same thing could happen with k minus 1 also, right?
No, so here, just give me a moment. Okay, what is this? So there is this issue with Zoom. It used to give me like unlimited time for my first meeting, but it's not doing that now. So I think you guys will have to join again for another meeting if that's okay for you. So this meeting is going to end in 10 minutes. Yeah, so Nidish has basically answered your problem. So let's just quickly code this up and then we'll do another meeting. So is my Sublime visible to you guys? Can someone?
Yes.
Yeah, okay. All right, so we have to do combinations. So let's just copy this template of NCR values. So I hope I don't need to explain how we calculate combinations. So now let's just go to the coding part. All right, so let's look at the input. We have NK and then we have these values. Sure. Let's take in the vectors. Although I'm going to write the exact same code that I had before, but still it's a good practice to just submit everything so it all makes sense. So now we'll individually sort these values of LNR. Yeah, so there was no need to take them separately. We could have taken them together and then we could have distinguished by some variable that whether it is a starting point or an ending point. But that makes this implementation easier if we just take them separately. There is also another method to implement this via maps, and I'll show you that method in the next problem. Okay. All right. So let's take this variable on, which is denoting the number of lamps which are on right now. And then we have I and j. Initially, both of them are 1. Okay. So while I is less than equals to 1, n and j is less than equals to n. And then we'll simply check if L of I is less than equals to R of I. Notice that I'm giving priority to L of I because these R of I values are not inclusive. So now if the number of lamps which were on was previously greater than or equal to k minus 1, then I will add something to my answer. Okay, so we also have to change this mod value. Yeah. So we will add this expression. So the number of lamps which are on, Ck minus 1 to our answer. And then we have to do lamps plus plus and I plus plus. Sure. So
Now at this point,
yeah.
If that L of I is equal to R of I, don't we have to do lamps minus minus also?
Sorry, what? I missed your problem. Can you repeat?
If L of I is equal to R of J, that means that if at L of I, the value there, that is the point at which a lamp turns on, and R of J is where it turns off. If they are equal,
yeah,
won't we have to do an on minus minus or something?
Yeah, so that we have to do, and that I'll be doing in this else statement, right? So now here I'm doing on minus minus and j plus plus. So that will automatically handle
because
everything.
they are not inclusive, the endpoint.
Yeah, the endpoints are not inclusive. Yeah, that's the reason. Yeah, so I'm not doing Li is less than Rj because these intervals are not inclusive. So at Rj, this lamp strictly turns off. Okay. So yeah, this should basically do my job. Looks good to me. Let's just see if it runs. Okay, this is weird. Let's copy everything. Oh, it's giving 9. That's looks correct. 3 is correct. Okay, let's just submit. Yeah, so Kasparov, this problem is it's basically an introduction to the sweep line algorithm. So this meeting is going to end in like 2.5 minutes. So I think it's better if I just make a new link and share it with you guys, if that's not a problem. Okay, so this is working. So now what I'll do is I'll end this meeting and then I'll share a new meeting link with you guys. And we have 2 more problems. So I'm going to be a little bit quick so that we can finish both these problems in the next 2 meetings, in the next meeting. Okay. So yeah, I'll just end this meeting now. All right, so now I think we can start with the second problem. And interestingly, this problem is 90% the same as the previous problem. And I don't know why this problem is rated 2000 and the previous one is rated 1800, but we'll see that this problem is basically the same as the previous problem. So I'll be really quick with this one, and then we can give time to the next problem. And also, this problem I'll be implementing the sweep line technique, not using vectors, but using maps, which is a much more convenient way to do it. Okay. So yeah, let's start with this problem. So in this problem, basically we again have these n intervals, and these intervals start at L and end at R. This time they are inclusive, and the f of an interval is basically the number of elements which are present in this interval. So f of an interval which starts at L and ends at R is equal to R minus L plus 1. Okay, and so we have n and k, and then we have n intervals. And what we want to find is, for all the subsets of size k out of these n intervals, we have to find the value of f of the intersection of that particular subset. Okay. So in other words, we should find the sum of the number of integer points in the intersection of any k segments. So out of all the nck subsets of size k, we have to take the intersection of all the k intervals in that subset, and then we have to add the length of that subset to our answer. Notice that in the previous problem, we just had to find out the number of ways. Notice that in the previous problem, the contribution was 1. So if we had a subset of intervals whose intersection was non-empty, we would simply add 1. But in this problem, if we have an interval whose intersection is non-empty, then we will add the length of that interval to our answer. So that is the only difference between the previous problem and this problem. Rest, everything is exactly the same. So I'll just give 2 minutes to think about this problem, and then we can discuss various approaches. Yeah. So if you have anything in mind, you can unmute yourself or maybe write it in the chat. Otherwise, in 2 minutes, I'll start with the solution. So any approaches? This is not much different from the previous problem. So only the expression is different, right? So in this problem, only the expression that we are adding to our answer will be different. So I just need this expression. Can anyone tell me what will be the expression? No ideas?
Can you explain the question? I mean, a little.
Yeah. So the question is that there are n intervals that we have, okay, and we will basically go over all the NCK combinations of choosing k intervals out of these n intervals, okay, and in every of these combination we will try to take the intersection of all the k segments that we have, and then we will add the length of that intersection to our answer, okay. So f of an intersection is its length, okay. In the previous problem, what we were doing is we were iterating on all these NCK combinations of choosing k out of the n segments. And if the intersection was non-empty, then we were adding 1 to our answer. But here, instead of adding 1, we have to just add the length of that intersection to our answer. Okay, that is the only difference between this problem and the previous problem. So is the problem clear to everyone? Okay, great. Yeah, so how are we going to approach this one?
I think we need to have like the first value at which the previous segments are ending, the lowest value.
Mm-hmm.
And then we can, like, if we are fixing a segment
Mm-hmm.
from which we are starting and the lowest value at which the previous segment is ending.
Mm-hmm.
So we can choose any k of them.
Sure, sure, sure.
And then into the length of those.
Great, great, great. So this is the entire solution. So very good. This is exactly what we are going to do. Okay, so I'll give 2 more minutes to think about it. And if anyone has anything to say, you guys can say it. Otherwise, I'll just code it up and I'll explain on the go. So anybody else has any inputs? Yeah.
We can store li. We will be taking the when the same conditions will be coming. If li is less than ri, we will take the maximum for the left hand side ones, and we'll take the minimum for the right hand side one, and we'll take the difference minus the difference plus 1.
Okay, okay, makes sense, makes sense. So okay, so let me just give a brief overview of what I'm going to be doing that is different from what I did before. Okay. So let's say we have again sorted all these 2n values in a vector, and let's say the first element in this vector is 0 and the second element in this sorted vector is 5. So yet again, I am using the same example. So previously we argued that the situation between x equals to 0 and x equals to 4 remains exactly the same, right? So what happens is that let's say between x equals to 0 and x equals to 4, there are m intervals which are turned on. Okay. So if this value m is greater than or equals to k, then we can say that the number of intervals which are turned on is greater than or equals to k. And okay, so is there the notion of k here? Yeah. So we have to choose a subset of size at least k, right? So if the number of intervals which are turned on are greater than or equals to k, then basically previously we were just taking the number of intervals which were on ck, and that was the value that we were adding to our answer. But here the thing is that instead of taking 1, we have to add the length of this interval, right? So basically we will have the contribution of each point. So we will have the contribution of each point x equals to 0, 1, 2, 3, and 4 instead of just x equals to 0. But the thing here is that the contribution of all these points will be exactly the same because the situation is exactly the same, right? So we can just find the contribution of x equals to 0 and multiply it by 5 because there are 5 points here, right? Make sense? And the value of the contribution remains exactly the same as it was before. So what we'll do is we'll simply add 5 into mck to our answer. And this is the only difference between this problem and the previous problem. So I hope this is clear enough. So do you guys have any doubts? If not, then I can go and quickly code this solution up. And this time I'll use the map-based implementation. Okay. So yeah, let's jump to the code. Can you take a short example and show how things are working? Okay. So let's have a look at the samples. So let's say we have a situation like this. So if we sort all these values in a vector, what we'll get is we have 2 1s, and then we have 2 2s, and then we have a 3. Okay. So at x equals to 1, we notice that there are 2 intervals which are turned on, right? The first interval and the second interval. And the value of k is greater than or equals to 2. Okay. So we are here at x equals to 1 right now. And we notice that there are 2 intervals which are turned on. And so basically there is just one way to choose 2 intervals out of these 2 intervals. So at x equals to 1, we add 2c2 multiplied by 1 to our answer. Now, why did we multiply it by 1? Because the next relevant point is x equals to 2. And there is no point between x equals to 1 and x equals to 2. Okay, so that is why we are simply multiplying it by 1. Now, we notice that at x equals to 2, this first interval has ended and this second interval has started. So we again have 2 active intervals, right? So now we are here and we again have 2 active intervals. So we'll again add this same expression to our answer. And we will again multiply it by 1 because the next important point is x equals to 3 and there are no points in between them. If this point was, let's say, 5 instead of 3, then we would have multiplied this expression by 3 for x equals to 2 because there are like 3 points between 2 and 5, that is 2, 3, and 4. And the contribution of all these points will be exactly the same because the situation is exactly the same between x equals to 2 and x equals to 4, right? So this is what is happening. I hope this made things a bit clearer.
Segments are inclusive, right? So we will
Yeah, this time, yeah, segments are
multiplied by 4, not 3. We should multiply it by 4, right?
No, so we will multiply it by 3 because we only are considering 2, 3, and 4. At x equals to 5, the situation is changing, right? At x equals to 2, 3, and 4, the situation is same. But at x equals to 5, the situation will change. So we will multiply it by 3 instead of 4.
But
right?
5 is also included in that, right? Like the previous segments are ending at 5.
5 is included, but
R minus L plus 1, I guess.
No, like at x equals to 5, let's say if a new segment was starting, then we will, like, things are changing at x equals to 5, right? That is what I mean to say.
Another one can start. Yeah, you're right.
Okay.
We'll take it separately.
Yeah. Because there is no harm in taking it separately.
Because new segments can add in there.
Yeah. Okay, so let's jump to the code. All right. So we have K, L, and R. So this time I'll use a map. So what I'll do is I'll keep this map and let's say I call this map active. So active of I will basically denote the number of segments which are active. That means the number of segments which are turned on at the position x equals to I. Okay. So this has the definition that you expect. So now we'll read in L and R. Now what will happen is that an interval is starting at L, right? So I can just do active of L plus plus. And if an interval is ending at x equals to R and R is inclusive, that means that till x equals to L and x equals to R, this interval stayed. But at x equals to R plus 1, this interval ended. So I can do something like active of R plus 1 minus minus. So if you guys have read about this concept of the difference array technique, then this is very simple. This is very similar to that. We are just making a difference array in the form of a map. Okay. Now we can also have a vector which stores all the important points that we have, all these 2n points in the worst case. So we'll go over the map. And we will basically push all these points into our map. So endpoints dot push back x dot first. So all these important points are also in the vector. So we'll see how we will use this vector later on. So let's keep a variable, let's say cur. So this denotes the number of segments which are turned on right now. Okay. Now I will iterate through all of these points as I did when I was dry running that test case. So I will go from 0 to size of endpoints minus 2. Now I have endpoints of I and I have endpoints of I plus 1. And between these 2 points, the situation is exactly the same. Okay. And I also have to maintain the number of segments which are turned on. So I will do something like cur plus equals to active of endpoints of I. At x equals to endpoints of I will just do cur plus equals to active of endpoints of I, and that will magically give me the number of segments which are active. So this is basically just an example of the difference array technique. I think most of you already know it, so it would be easy to understand why this will give me the number of segments which are turned on. And let's say I have a variable size which is equal to the number of points between these two values. So it would be endpoints of I plus 1 minus endpoints of I. Notice that these endpoints are obviously in sorted order because I am taking a map, and a map is automatically making everything sorted. So then I just have to check if the number of segments which are turned on is greater than or equals to k, then I will add the expression to my answer. So answer is answer plus. So first of all, what I'll do is I will choose k segments out of these cur segments, right? And I will multiply it with this size, because the contribution of each element between endpoints of I plus 1 and endpoints of I is the same. Okay. So yeah, this is what I'm going to do. So this should hopefully work. Yeah, so let's just submit it. Okay, so seems to be working fine. So does anybody have any doubts here, or should I move to the last problem that we'll be doing? So the main thing here is to understand why I am multiplying this expression by this endpoints of I plus 1 minus endpoints of I. And also to understand this difference array thing, but I think that is trivial. So Sumit is saying, why didn't we do cur c k minus 1 in here? Because this time, basically, we are looking at all these points which are in between endpoints of I plus 1 and endpoints of I as a separate interval, right? So the contribution we are adding the contribution of all the points which are between endpoints of I plus 1 and endpoints of I. And to do that, the expression would obviously be cur c k. Okay, great. So I think there are no more doubts. So we can go to the last problem that we'll be doing, which is much more interesting, because that is not just a blind use of sweep line. It involves something else as well, and it would be really interesting. So yeah, let's move to the second problem now, the third problem. This is from Code Forces round 536, problem E. I'll just share the link in the chat. Okay, so let's read the problem. So we consider a timeline from t equals to 1 to t equals to n. And in the ith red envelope, it will be available from time si to ti. So there are some envelopes, and the ith envelope is available from t equals to si to t equals to ti. And all the times are from 1 to n, which is a good thing here because n is up to 10 to the 5. We'll see how to use that later. Inclusive. And a particular red envelope contains wi coins. Okay, so if Bob chooses to collect the coins in the ith envelope, then he can do it only at an integer point of time between si and ti, obviously, because that envelope is available only between these two time intervals. And he can't collect any more envelopes until time di. So that is another interesting thing. So if the person chooses to collect the ith envelope, then he can't collect any envelope at a time instant before t equals to di. Okay. And obviously di is greater than or equals to ti. Now, Bob is a greedy man. He collects coins greedily. So whenever he can collect coins at some integer time x, he collects the available red envelope with the maximum number of coins. So if there are multiple envelopes with the same maximum number of coins, he would choose the one whose parameter d is the largest. And if there are still multiple choices, Bob will choose one from them randomly. Okay. However, Alice, his daughter, doesn't want her father to get too many coins. So she could disturb Bob at no more than m integer time moments. And if Alice decides to disturb Bob at a time x, then he could not do anything at time x and resumes his usual strategy at time x plus 1, which may lead to missing some red envelopes, obviously. So we need to calculate the minimum number of coins that Bob would get if he continues using his greedy strategy, but Alice disturbs him at some of these m coins greedily, optimally. Okay. So the problem statement is a bit involved. And that is the reason why I share the problems before the start of the session, a few hours before. But still, if you haven't read it, I think it's not very difficult to understand. So if you have any doubts in understanding the statements, do let me know. Otherwise, I'll give you 5 minutes to think about it, and then we can look at the solution.
Suppose
Yeah.
if the values of S and T are 3 and 6,
Okay.
and value of D is 10.
Okay.
So if you pick that envelope between time 3 and 6, so can you pick another envelope in between time 3 and 6?
Yeah. So if can you repeat your question? Can you repeat the last line?
I mean that if there are two envelopes that have the same interval but different DIs, so can you pick the both envelope at that time interval?
Yeah, that's totally fine. So if there is another envelope which has S and T as 3 and 6, but it has D is equals to, let's say, 5. No, that can't happen. Yeah, so let's say it has D equals to 9. Then if I pick the second envelope, then I won't be able to pick the first envelope because I can only resume my picking from T equals to 9. And at that point, the first envelope would have already finished. Okay. Can you explain one example? Okay. So let's look at the first example. So yeah, here M is 0. So there is no concept of disturbing. And K is 2. What is K here? Okay, so the total number of envelopes. Yeah, so there are these two envelopes. The first envelope starts at t equals to 1, ends at t equals to 3. And okay, so just give me a moment. Yeah, so its d value is t equals to 4. And also the number of coins that I'll get is 5. Okay. And the second envelope starts at t equals to 2, ends at t equals to 5. Its d value is 5, and we would get 8 coins. Okay. Yeah. So now let's see the optimal strategy that we'll have. So what we can do is, there is no concept of disturbing here. So Bob will basically collect the coins in the red envelopes at t equals to 1 and t equals to 5. Because at t equals to 1, he'll choose the coin, and then he can't choose any other coin between t equals to 1 to 5. So at t equals to 5, the second coin is still active. So he will choose the second coin as well. So in total, he'll be able to choose both the coins. But let's say instead of 5, this value, instead of 5, let's say it was 4. So in that case, I could not have picked this second coin if I picked the first coin. So the optimal strategy would have been to pick the second coin itself and get 8 coins in total. So pick the second envelope and get 8 coins in total. So I hope.
We can't pick the second coin because we're choosing greatly here.
Oh yeah. Sorry. Yeah. So that's true. Wait a minute. Yeah, so that's true. So we have to choose the first coin only, right? Because the man is greedy and his strategy is basically fixed. So is the problem statement clear now? Okay, so I'll just give 4 to 5 minutes to think about it, and then we'll look at the solution. Here, the good thing is that there are no huge values, so we can look at every time instant separately, and we don't have to do a lot of complicated things. So that is a good thing here. So does anybody have anything in mind how we can solve this? So just forget about what Alice is doing and tell me how we can calculate this value. This value that Bob will do for every time instant. Anything?
We will just sweep through the instance and see if the current time is valid or not.
Yeah, so we will be sweeping through all the time instants. And basically what we'll do is we will find out of all the coins which are active, which coin has basically the maximum number of coins. Which envelope has the maximum number of coins. And also out of all the envelopes which have the maximum number of coins, we will look at the one which have the maximum value of D. Okay. So how can we implement this? How can we maintain something in such that we will quickly get to know which is the coin which is the envelope which has the highest number of coins? So this is not a very difficult problem.
Set or multi-set.
Yeah. So that is what I was saying before, that we will maintain some information in a data structure and then we will sweep through all the time instants. And the data structure which is optimal here is a multi-set of pairs. And that is going to help us.
Multi-set, we will store like the number of coins and that parameter, right?
Yeah, so we'll store number of coins and D.
And we will pop it out from the end. For the
yeah, so maybe it's better that we negate it and then we can pop it from the beginning.
Yeah, we can negate and push it.
Anything works, but yeah.
Looking at the constraints, it seems like this M, we can put it like this: at any instant time t, if Alice makes J disturbances, what is the minimum? I'm not sure about the transitions and all this.
Yeah. So that is totally right. So looking at the constraints, M is really small. So again, we have just 10 minutes. So I'll give 5 minutes to explaining and then I'll code it up in 5 minutes. Okay. So looking at the constraints, what happens is that since M is only 200, a solution of O of NM will pass. So what we can do is we can have a knapsack kind of DP. And the state of the DP will look something like this. So first of all, we will pre-compute using sweep line. For each time instant. the coin that the envelope that we are going to buy. Okay. So then we can do a DP. So how the states of the DP are going to look like? So we'll have a simple 2D DP and we'll do something which is very similar to a knapsack. So this is the minimum number of coins I can get if Alice disturbs, so Bob can get. If Alice disturbs her exactly j times in the time interval from 1 to I. Okay. And so the final answer is going to be nothing but DP of, so it's going to be minimum of dpn1, dpn2 up till dpnm, right? So does this make sense to everyone?
Yes, yes.
Yes.
And what about the transitions? So let's see how we can make the transitions. So for each time interval, we are basically maintaining two values, and these values are coins of I, which is the number of coins Bob will get if he takes an envelope at t equals to I. And the second thing is that is this variable called next time of I, which is basically the D value. So it will be the time that I can resume. So it's the time that Bob can resume taking envelopes if he takes an envelope at t equals to I. So now the transitions are basically just very easy. So the first choice is that, let's say I'm at dpij and I decide to not take, so I decide that Alice disturbs Bob at this point. Okay. So then from dpij, I can basically go to, so basically I'm at dpij and then I'll go to I plus 1 and j plus 1. Why? Because Alice is disturbing Bob, so he is not taking anything. So he can resume with his usual strategy at t is equals to I plus 1. And then Alice would have disturbed her j plus 1 times. So we'll do dp of I plus 1, j plus 1 is minimum of itself and dpij. Okay. And the second thing is that Alice doesn't disturb Bob. So if she doesn't disturb Bob, then he will necessarily take a envelope because that is the greedy strategy that he's following. So now if I'm at t equals to I can only resume taking coins at next time of I, right? Which is a value which I have already calculated. And this j remains the same because Alice is not disturbing Bob. So this will be minimum of itself and dpij plus the number of coins that I get from the ith envelope. Okay, so these are the two transitions that I have. I hope these transitions are clear. So does anybody have any
Can you
doubts?
explain these transitions once again?
Yeah, so the first transition is that Alice disturbs Bob at t equals to I. So if she disturbs Bob, then from ij, I will go to t equals to I plus 1. Why? Because he can just resume his usual strategy at t equals to I plus 1, right? And the number of times Alice would have disturbed her would increase by 1 because she is disturbing her at t equals to I. So I'll go to dpi plus 1 j plus 1 from dpij, and also I will not have got any extra coins, so I can just minimize it with dpij. And the second case is that Alice does not disturb Bob. So at this in this case, I will resume my usual strategy at next time of I, which is a value that I have previously calculated. So then from I will go to next time of I, and j will remain same because Alice hasn't disturbed Bob yet, right? So then I'll go from ij to next time of I and j, and also I will get coins of I extra value. So I will minimize this with itself and dpij plus coins of I, right? Does this make sense?
I have a question.
Yeah.
Like if Alice disturbs Bob at time I, does it stop him from taking an envelope at time I or next time of I?
Yeah, so if Alice stops Bob, then it stops Bob from taking an envelope at t equals to I. So he will go to t equals to I plus 1, and Alice would have disturbed her one more time. So j becomes j plus 1. And in the second case, Alice is not disturbing Bob. So that means Bob is taking a coin. So then I can resume taking coins only at next time of I. And then the number
But
of...
what if she disturbs him at next time of I? It will be a value greater than I, right?
Yeah, so if Alice disturbs her at next time of I, then that is something I am taking into account, because I will go to all combinations of I and j, right?
Yeah. In the later transitions.
Yeah. So
And
yeah.
that coin array you're calculating. So in that case, you are not considering the Alice part, right? Only just the
Yeah. That I'm just considering that there is no notion of Alice. So taking that into account, Bob will just follow a greedy strategy, and then that would be easy to compute. So I won't be able to code this up because of lack of time. There is only 3.5 minutes. So I'll just show you guys the code, and then we can discuss the doubts quickly. So the code goes something like this. So first of all, I create a vector of vector where I store all the events, right? So event is basically starting of some envelope or ending of some envelope. And then in events of S, I'm basically pushing back 1, minus W, and minus D. 1 means that an envelope is starting, and W and D are as described in the statement. Similarly, in events of t plus 1, I am pushing back 0, minus W, and minus D. 0 indicates that the envelope is ending, and W and D are the same as before. And this is t plus 1 because the intervals are inclusive. And then I am creating this multi-set of pairs, which I had previously discussed. And I have these two vectors, coins and next time. And then I iterate for all the time instants from 1 to n. And I look at all the events which are happening at this time interval. So if it is an event where an envelope is starting, then I insert these two values in my set. And these two values are W and D. So minus W and minus D. And if an interval is ending, then I'm erasing these values from my multiset. And this is how I'm doing it. So if the size of the multiset is 0, that means there is no envelope which is available to me. Otherwise, I will just take the ones which have the maximum value of coins, and out of those, the ones which have the maximum value of D. And coins of I will be IT first, and next time of I will be IT second. Okay. So this is how I calculate coin and next time. And then I do a simple DP. The transitions are as described below. So the first case is that Alice disturbs Bob, which is the transition that I wrote previously. And the second case is that she doesn't disturb Bob. And also, if coins of I plus 1 is 0, that means there is no scope of taking a coin. So that remains same. So DP from IJ, I will simply go to I plus 1J. And that's it. So I'll just take all the DP values from DPN1, DPN2 up till DPNM. And that is my answer. Okay. So this is the code. So we still have 1.5 minutes. So if there are any doubts, you guys can ask.
Will you upload this on YouTube?
Yeah, sure.
Sir, can I ask doubt?
Yeah, sure. Sure. Go ahead.
Sir, so basically my rating is around 1200 on CF. So what should I do now? Means it's from 2-3 months. Should I increase my practice or more, or should I learn new topics?
I mean, I think if you have already done binary search and basic dynamic programming, and you have solved a few constructive problems, then I think you should just practice and not learn anything new, right? Also, I think we are a bit out of time, so the meeting will end any second. So thank you so much for joining, everyone. And I will see you in the next session, hopefully on another interesting topic. So yeah, that is it. Bye-bye.
Bye.